Swayam Prabha. Digital India. Educated India.
So, in this lecture, I would like to continue our discussion on mechanical properties of polymers, especially solid polymers. If you recollect from the previous lecture, we are talking about stress strain relationship for a given material, and then we looked at various various quantities that characterize materials. We were talking about yield stress, ultimate strength, rupture. We also showed one video how these experiments are done. Okay, so building on that, we will discuss a few more properties. So now, before we go to polymers or plastics, we can look at metals, because metals are very well studied and we know its behavior quite well. Generally, for a metal, think about copper or iron, one of those metals. Generally, when we try to apply a load, when I say load, I mean that you apply a tensile load, you try to deform it. And then if you try to measure the stress, that is force per unit area, and the deformation, which we call strain, usually it follows a linear relationship. The stress is proportional to strain, and the proportionality constant is the is basically the Young modulus, right? And pictorially, we represent the material to have something like a response similar to a spring. Okay, so think about a spring. When you apply a load, fix one end of the spring, and you apply a load in another end of the spring, you will see that depending upon the load, the spring extends. Okay, so this is something, a very good example of a mechanical model of representing how a material will behave. Okay, so just like how a spring expands for a uniaxial load, materials also, when you apply a load, when you apply stress, they also deform. For metal, we can easily understand this because we think about metal as a crystalline material. Okay, we got atoms located in lattice points, and there is some sort of a vibration about the lattice points. So when you try to apply a stress on this material, you are basically trying to replace the atomic positions, but then the atoms wants to come back to its original lattice positions. So it kind of gives a very spring-like action, right? So therefore, many metals generally behave this kind of a Hookean solid, okay, an ideal solid, where stress is proportional to strain. So when we think about metal, we think of a mechanical model, which is basically a linear spring, as I said, and the spring will have, you have a stiffer spring, you have a flexible spring. Some of the spring that you are using in your pen, those are much more springs with a less modulus, right? So it's easy to deform. There are other spring which can be very hard to deform, especially the spring that is used in car suspensions. If you see, those are much more stronger. You need to apply a lot of load to change this deformation. Okay, so springs can have a spring constant. Telling the spring constant signify how easy or how hard it is to deform the spring. Similarly, materials also will have this kind of a property which is called Young modulus, that tells how strong, how stiff this material is, how difficult it is to deform this material. Okay, so typically metals will have very high Young modulus, right? And so generally what happens is that when you try to so this Hooke's law, or the linear spring model, says that if you try to apply a load and immediately there is a change, you see immediate deformation. But sometimes we apply load at a high temperature, or sometimes we apply at room temperature, but over an extended period of time. Okay, so in this case what happens is this deformation or elongation will continue over time. Okay, because you are sustaining this load for a very long time, or maybe you are going to a very high temperature, you are applying a load. In both of these cases, the elongation will not be immediate, but will have a history. Okay, it will change over time, and we call this as creeping, okay, or the creep response. This is basically that the material under tension, under tensile force, over a period of time will continue to deform, and we call that as a creeping behavior or creep behavior. And when you have this kind of very slow response over time, a simple model like this cannot simply explain. Okay, So, especially the time dependent deformation, we cannot explain those kind of behavior with a simple Hooke's law. We need better models. Okay, we need models that are more than this spring like models, right. So, as far as metals are concerned, typically this is what happens, that you apply a load, it immediately takes some deformation, but then if you continue to apply this load for a very long time, or you do this at a high temperature, the material will slowly evolve in time. Okay, so then you need a little better model than simple springs. Now, if you go to plastics or polymers, in this case the creep behavior, which means the slow evolution of the strain, is actually more pronounced in thermoplastics and rubber than metals. So, metals also can show creep behavior, but plastics can show creep behavior much more, okay, but much more pronounced. Typically, when you think about a mechanical model for this kind of plastics, they involve this kind of springs which highlights this elastic like behavior. In addition to that, there is also called viscous effect, which is represented by a dashpot, which kind of dampens out the effects. So, that combined together we call them as a viscoelastic models. So, metals mostly we can work with a Hookean solid model, which is a linear spring. When you come to plastics, okay, plastics show more pronounced creep behavior. To explain creep behavior, you think about combination of springs which represents elastic response and the dashpots which represents viscous modes. And why we need this kind of mechanical model or viscoelastic model for polymer is that we can actually find their flow behavior in melts of polymers, especially when you try to extrude them, or when you do injection molding, or when you try to look at some other thermal process. As you would have seen in the industrial visit, plastics are mostly heated, okay, they are all subject to thermal stress. What happens is that they melt, then they flow. So, under different temperatures, how the flow behavior of the plastic melt or the plastic itself is very important. To study that mechanical behavior, you need this kind of models, okay, which we call them as a viscoelastic models. Broadly speaking, if you have a solid material, typically elasticity or elastic effects will dominate. The moment you go to melt state, where the polymer is melted at melting temperature and it's going to be very viscous, highly viscous. So, here the viscous effect will dominate, but in addition there can be some elastic effects also. So, that is why we call them as a viscoelastic model. It has a behavior of both viscous effect as well as elastic effect. So, this viscoelastic models are more important for plastics that are melted, that are used in this kind of injection molding, extrusion and various other thermal processes. Okay. So, I want to now give some examples of some simple models that we can use to characterize plastics under thermal conditions, and then try to characterize their properties. So, the most simple model is called this ideal solid or ideal elastic material, which we already talked about. It follows this kind of stresses proportional to strain, which we call them as a Hookean solid. The mechanical model is like this: the string is attached to one particular surface, and then you apply a load on the other end, then the spring will expand. To what extent it will expand is given by this Young's modulus, right. So, if you compare between two material, okay, and if you apply the same load, and if both of them expands same distance, that means they both have the same Young modulus. The one that has higher Young modulus will deform little, okay, because you can see this epsilon here is given by sigma by E. For a constant load, if a material has higher Young modulus, it will deform less, the strain will be produced lesser extent. If this Young modulus is less, then this strain will be more, okay. So, the Young modulus here means the stiffness, how stiff this material is. If it is more stiff, it will elongate little. If it is less stiff, it will elongate more for the same load, right. So, most of the elastic behavior, purely elastic solids will follow this Hooke's law. Then you have the other limit, purely viscous, no elastic component, purely viscous. So, that is shown by this kind of a dashpot model, right. So, here we show that the stress is proportional to not the strain but the rate of strain rate, and the proportionality constant is called this viscosity. Have you seen this formula before? Is it familiar to you, this equation? What is it called? What is this equation called? Huh? Model modulus of elasticity. No, you would have seen this in fluid mechanics. Newton's law of viscosity, right? Newtonian fluids, we characterize Newtonian fluids, ideal fluids, right, with Newtonian so usually we write tau xy is equal to minus eta dv by d, something like this, right? The same expression is now written in terms of stresses and strain rates. Okay, so this equation is nothing but Newton's law of viscosity, which characterizes Newtonian fluids, in which case if you apply a strain alone, the material will not respond. But if you apply a strain rate, that you keep changing this deformation over a period of time, when you apply a strain rate, then the stress will be proportional to that. Okay, so this is a behavior of a pure viscous effect. Okay, and this viscous effect is captured by this viscosity, right? And so this is something more intuitive. You have let us say if you have two liquids, one is more viscous than the other. Okay, so here to what extent if you apply the same strain rate, right, the one that has higher viscosity will have more stress developed. Okay, so these are the two extremes: ideal elastic behavior, ideal viscous behavior. Okay, but polymer is something in between. It has viscous effect, it also has elastic effect. So you can think of the models for polymer should be some combination of these two, so that it can have some elastic response as well as some viscous effects. Okay, so that basically takes us to what's called this Maxwell model, very simple but very widely used to capture this viscoelastic behavior of plastics. So in the Maxwell model, basically we have a serial combination of a spring to capture the elastic effect and then a dashpot that captures the viscous effect. Okay, so the total strain that is generated in this body, in this model, will be a sum of the strain developed because of the elastic part and plus the viscous part. So you can see the total strain is sum of strain developed due to the spring, elastic contribution, and due to the dashpot, which is coming from this viscous effect, right. So you can see that this is the model for ideal solid, this is for the ideal viscous material. So now we have put them together in a series. Okay, so they both combinedly support the applied load, so that the strain is a sum of the strain from each part. So then what we can do, we can take time derivative of this expression. So the rate of change of total strain is nothing but the rate of change of strain due to spring plus the rate of change of strain due to dashpot. And so from here, if I take the time derivative of this, you will see that I am putting this dot to say this is t sigma by dt. Okay, this is a time derivative. So you will see that sigma dot is equal to E is constant plus epsilon. Okay, so from here I can write this epsilon dot is nothing but sigma dot divided by E. Okay, so this comes from the elastic part, whereas for the dashpot we already know that the stress is proportional to strain rate. So we can directly write eta dot here is sigma by eta. Okay, so that's what is being substituted here. So now this is a kind of a model which tells you how strain rate is proportional to the load, the rate of change of load, the Young modulus, and the viscosity. Okay, so we are thinking about a polymeric material that can have elastic response as well as a viscous response. The elastic response is captured by the Young's modulus of the material, and the viscous part is captured by the viscosity, right. And then we have a model, mechanical model here, where the total strain is a combination of strain due to the elastic part plus the viscous part. Okay, so now we can think of two kinds of mechanical testing. One test involves where you apply a constant load and you look at how strain changes. Okay. So, that is called the creep test, where you apply, you take this material, you subject this material with a constant load. That basically means putting a weight, applying a load, and then looking at how the deformation will happen. So, the deformation and strain I am using interchangeably. So, now you can see what this model will yield when I have a creep test, which means I apply a constant stress or a constant load and I am interested to the response of the strain or the deformation. So, what we do here is that in this equation, since sigma is constant, sigma dot, the time rate of change is 0 because sigma is constant. So, the first term will vanish, then the remaining term would be just simply sigma by eta. So, I am just basically rewriting this epsilon dot as d epsilon by dt, that is equal to sigma is now written as sigma naught because constant, and viscosity is also constant. Okay. So, from here if you integrate this with respect to time, you will see that the strain is equal to some constant plus sigma naught by eta times t. Okay. It basically says that when I have a Maxwellian kind of a material which has this combination of spring and a dashpot, when I apply a constant load, right, over a period of time, the strain will linearly increase with time. That is what this means, right. So, here it is shown pictorially. So, we have a creep response, which is the integrated equation that I showed in the previous slide, and so here on the on the x axis we have time. So, you can see the stress was 0 and then suddenly you apply a load here and then you keep it, that constant load, over a period of time. Okay. Then what happens is, there is a material, when you apply suddenly this load, it jumps to some initial epsilon naught, which is equal to sigma naught by E. This I am writing because I know that the material is having some elastic behavior. So, this immediate thing that you see is a elastic response, and after that this epsilon will grow proportional to this sigma naught by eta. So, this slope here is sigma naught by eta. It continues to grow, it will keep on growing, but in this experiment at some time Ts we have withdrawn the load, we have removed the load. Okay. Once you remove the load, then you can see that the material will start relaxing. So, you can see that immediately drops to a terminal value, which is given by sigma naught Ts by eta, which is basically nothing but this. If you substitute T equal to Ts, that is your epsilon value, right. So, a typical Maxwellian material will respond to a creep test in this particular way. Okay. So, again recall that creep test basically means subjecting the material for a constant load and looking at how deformation or strain will evolve with respect to time. So, creep test is looking at the material, how it responds over time for a subjected conditions. Typically, we keep the temperature, humidity and various other things constant here. We apply only a load and we look at how the deformation changes, right. So, a Maxwellian material will show this kind of a behavior. So, you can see that there is no real response here. When you apply this load, the initial strain jumps immediately, there is no lag, it responds immediately. Similarly, when I remove this load, you can also see there is a sudden jump, the material is able to respond immediately. Okay. So, there is no delay in this response. So, this is an ideal material. Sometimes they will not happen, they will not behave like this. There will be a small dynamics here as well as there will be a small dynamics here also. Okay. But as far as this Maxwell model is concerned, this is how you would expect the material to behave under constant load. You can also note that this height and this height are the same thing, because these both are elastic response, which immediately shoots up and shoots down when you remove this stress. Now, we can also have another experiment where you can actually say that you can apply a strain and then look at what happens to the stress, right. The creep test is where you apply a constant load, constant stress, and then you look at how the material will deform over time. So, here we actually keep this strain constant, you stretch it and then keep it at certain position, so that the strain remains constant. Then the material will respond how in terms of stress. Okay. So, we can go back to the model, Maxwell model that we derived, and then here we can say what happens when we keep the strain constant and look at the response of the stress. So, when strain is constant, this term is 0, strain rate is 0. Okay. So, then the right hand side, so we can write this entire term is equal to 0. So, this sigma dot is, so we can change this, we can separate the variables. So, that means I can write sigma dot by E is equal to minus sigma by eta, and then I can bring this sigma to the left. So, I will have sigma dot by sigma is equal to minus E by eta, okay, and that is what this equation is. And then you can write that sigma dot is nothing but d sigma by dt, and you can separate the variable d sigma and dt, and then when you integrate this on the left hand side, you will have ln of sigma by sigma naught, and the right hand side you will have minus e by eta times t. And then if you rearrange, you can show that the stress, when you have a constant strain experiment, the stress will relax exponentially. Okay. So, that is what this means, and you can also see that we have a new constant here which is called lambda, defined as the ratio between the viscosity to the Young's modulus, and we call that as a relaxation time. This is a material property. A material has a particular viscosity and its Young's modulus, and this ratio is called relaxation time. It will have units of time. It tells you how quickly the system responds to this imposed strain. So, in terms of picture, it is shown here. You can see that at some time t, we suddenly have a step jump in the strain. So, we give a constant deformation to the material, and then we hold it over a period of time. Okay, strain remains constant. Then we look at what happened to the stress. So, because of this strain, there is a sudden development of stress due to elastic response, and then the system also dissipates. There is also viscous effect, and the stress will be slowly dissipating. It is relaxing. It is called stress relaxation. Okay, and this behavior is actually follows this equation, which is exponentially falling. Okay, so if you wait long enough, it will come to 0, right. So, the stress relaxation is captured by the time constant lambda, which is given by viscosity over the Young modulus, right. So, we are talking about two kinds of experiment. One is this creep test, apply a constant load, wait for the deformation to evolve as a function of time. The other one is called the stress relaxation. You impose a strain and look at how the material's stress is evolving with time. Okay. So, both are very important, and we will probably see some more models. So, here is another model which is most common for polymers, plastics. It is called standard linear viscoelastic solids, or Zener model. So, I will not show the derivation of this equation, but I will tell you pictorially what it means. So, here this entire polymer plastic that we have, we are imagining that it has a spring E1, and then it is connected to a what is called this Kelvin arm, which contains a spring and a dashpot connected parallelly. Okay, this entire arm is connected serially with this spring E1. So, all this spring E1, E2 and the dashpot, they all have some physical meaning. Okay. So, this spring E1, you can think of is to have it is something that represents the resistance to the bending of the backbone of the chain, the polymer chain. Okay. As we know that the polymer is made up of repeating units of monomer, and there is a backbone, and the backbone can undergo a lot of this twisting motion, bending motion, right, and how stiff those chains are is captured by the spring E1, right. So, then we have this dashpot here that kind of represents or highlights the resistance to uncoiling under load and disentanglement of the chain. The chain can undergo a lot of thermal motion, okay, and there is a resistance to this, and that is captured by the dashpot. So, this is a motion by which the energy gets dissipated. Okay. So, that is represented by this dashpot, and then you have another spring E2, that is the thermal vibration that happens along the chain. So, for every molecular motion that you imagine that may be happening in the polymer, you could think of a mechanical model for that, okay. And this is one example where we combine springs and dashpots in a particular sequence in series, in parallel and in combination. You can actually derive many other models, okay. So, we are talking about only few set of them, and then once you have this kind of a dynamic model, how stress and strain rate, how they are all related, right, then you can have this equation, you can solve them for two of these tests, the creep test and stress relaxation, okay. In the case of creep response, where you subject this material for a constant load and then you look at how the strain will evolve, you can solve that equation and then you will get a response something like here, okay. And here we are introducing a new constant lambda c, which is defined as eta by E2, and we call this as a retardation time, okay. How many parameters are there in this model to characterize this model? How many parameters you have to specify? 3? Yes, 2 springs and 1 viscosity. So, this is called a 3 parameter model. How many parameters are there in Maxwell model? 2. In Hookean model? In Hookean model, how many parameters are there? Just 1. And Newton's law of viscosity model? 1. Okay. So, typically these models are represented based on how many parameters we need to specify. Okay. We may start with a simple Hookean model and you can see whether the response of the model, the material follows Hookean solid model or not, the creep test and the stress relaxation experiment. If it does not follow, you go to a little better model, you go to Maxwell model, where you have 2 parameters quantified, right, the Young modulus and the viscosity. Even if that does not work, you keep on adding more parameters, because maybe the entire material is composed of multiple modes of elasticity and viscous dissipation. So, here in this model, we are thinking of this material to have 2 kinds of elastic nature coming from 2 different molecular mechanisms, and there is one dissipative mechanism characterized by the viscosity here, okay. So, now here in this case, you can apply creep response, you can apply stress relaxation. So, what do we do in creep? You apply a load and measure the strain. What do we do in stress relaxation? We apply strain and we measure stress was a function of time, okay. Now, you can solve these models for these 2 conditions and you will get a response, and this is a model, this is the equation that will fit to an experimental data to see whether the assumed model that you have is able to characterize the material behavior or not, right. Many times these parameters would be a fitted parameter. Now, you got an analytical expression, you will use this equation to fit the data. From that you can actually get the parameters, the Young modulus, moduli, the spring constants, etc., right. So, that is how this equation become very useful in that sense. If the experimental data and this model fits very well, the fitting constants are basically your parameters, the viscosities and Young modulis. Any question at this point? Okay. Now, we also define few other terminologies called creep compliance. Creep compliance with this notation G of t. It is defined as the ratio between the strain of the creep test divided by how much stress is applied. So, remember, in creep we apply a load and we observe how epsilon is changing, how the strain is changing, okay. So, now this so basically we apply a constant stress. So, creep compliance is nothing but the ratio of the strain divided by the applied stress. In the model that I talked about previously, that SLVS model, the standard linear viscoelastic solid model, in that case you see that we already have a creep response. The creep compliance is nothing but epsilon divided by sigma. So, that whatever that you have on the right hand side, that is nothing but your compliance, okay. So, this entire thing is a creep compliance, and how we obtain this? We first substitute for epsilon of t from the creep response, divide by the applied stress. The applied stress is sigma naught here. So, you get creep compliance estimated by this. You can see that this is a quantity that changes with respect to time. So, creep compliance is not a constant, it captures the dynamical evolution of strain for a constant stress applied. Similarly, we can also think about a stress relaxation modulus E of t defined as the time changing stress divided by the applied strain, right, and that's a constant strain case. And again, if I go back to the previous model, so we have a stress relaxation response, I have sigma t, so sigma t divided by epsilon naught, that is the stress relaxation modulus, and you can show that this is also a dynamically evolving quantity with the characteristic constants like retardation time, the Young modulus E1, E2, etc. Right. So, here is a simple problem, you can try to solve this by yourself and I also do it here. So, what we have here is we have a plastic rod of 200 mm long and a diameter of 10 mm, and it is subjected to a constant axial tensile load. What kind of experiment this is? Is it a creep test or is it a stress relaxation experiment? Creep, right? A constant load is applied to a plastic rod, its dimensions are given. Now, after 100 seconds, its length is 200.5 mm. Okay, so it has basically increased 0.5 mm. Okay, what is the tensile creep compliance after 100 seconds? Okay, and we will come to this the second part later. So, what is the formula for the creep compliance? J is equal to epsilon over sigma applied, right. So, what is epsilon? We are talking about epsilon at a particular time after 100 seconds. Okay, so t here is 100 seconds. Okay, so this is L minus L naught by L naught. This is a definition of strain. So, what is L? That is 200.5 minus L naught is 200 divided by 200, right. So, basically it is 0.5 by 200. This is in so this is basically dimensionless quantity, right. And so then we need this sigma applied. So, how do we calculate sigma applied? So, this is force by unit area, right. Stress is force applied per unit area. How much force is applied? 400 Newton, right. Now, area is the cross section area. Since this is a rod, we assume it is a cylindrical rod, we say pi by 4 d square, right. So, pi by 4 into 10 squared. So, this is pi by 4 into 100 mm square. So, this is the area. Okay. So, then sigma applied would be 400 something like this. So, 16 by pi. So, now we can substitute that here, epsilon is 0.5 over 100 and this is 16 by pi. So, this is in millimeter square by Newton. So, this is your creep compliance. So now what is the use of this creep compliance? Okay, and that answer is given in this second part. If the load is doubled, okay, so you have done an experiment, right? You got a plastic rod, let's say it's an injection molded rod, right? And then you apply a constant load and doing a creep test, and you're making a measurement at 100 seconds. You measure the extension, how much deformation has happened. With this data, we are able to get this compliance at this point. Okay, so now you are asking another question. Let's say you do another experiment where you double the load. That means you go from 400 Newton to 800 Newtons. You're doubling it, and then you want to know what is the elongation, right? So here, what we can do here is we can use this creep compliance to answer this question instead of actually doing an experiment. Okay, since we have this information of creep compliance, we can say that epsilon will be J times sigma applied. So J we obtained from the previous experiment. We will assume that this is remain constant over this particular time, and so this is in mm square by Newton, and sigma applied. So what is sigma applied? It is 32 by pi, right? So can you solve this and tell me how much you get? So in this case, so if you use this creep compliance and then double the applied load, you can actually show that the length would be 201 mm for this particular experiment, right? So any question at this point? Yeah, you can go. Yes, yeah. Okay, so again, what we are talking about: Hooke's law, Newton's law of viscosity, Maxwell model, and then this 3-parameter model. Okay, SLVS model. Now we have the fifth one, which is called 4-element model. And the difference between the previous one and this one is that you can see there is an additional dashboard that is added. Okay, so if you look at this picture versus this picture, we have actually added one more dashboard here. Okay, and this dashboard is actually so this particular model, 4-element model, is typically used when you have a plastic in a molten state, when you have a melt, when you have a polymer that's melted, and then this melt polymer would have an additional mechanism of dissipation due to this molecular slippage of the chains. Okay, so if you want to apply for the same polymer, if you want to do in the solid state, you would just go back to the previous model, SLVS. Okay, but same polymer, if you want to do it in a melt state, you would add an additional dashpot. And here we have got 4 parameters: 2 spring constants and 2 viscosities. And so again, so in this case, the response for this model for a creep test would be given by this equation. So the way we derive this equation is, again, for the given 4-parameter model, we write the stress strain relationship, and then we integrate this equation. You get a differential equation, you integrate this equation for a constant stress condition, then you will get this creep response. So now I would like to show some actual data that how creeps data looks like, and how this becomes very useful. As we saw in the previous industrial visit, there was an R&D lab where different compositions are tested. Okay, and then you make an injection molding of that material, and then you go to study that property. Okay, so generally these plastic products are used for certain application that requires sustaining of some load. There is some mechanical load this material will also withstand. Okay. So, we need to study before we make in large productions. We generally take a small piece, injection molded or whatever you do, extrude it, and then you try to understand its stress and deformation profile. Okay. Or we do what is called this creep test. You take this material, apply different amount of load and look at how they deform. Okay. So, here what we have, so this on the left hand side what you see here is basically an injection molded polycarbonate plastic. Okay. It is a solid polymer. So, you take this polymer and you apply, if you consider one particular curve here, so a particular load is applied, let us say in this case some 41.5 megapascal tensile load is applied to this material, and then you measure how strain in the material is evolving. Okay. So, on the y axis we measure strain as a function of time. One material, one load is applied, and then you measure strain as a function of time. That is like a creep test. Okay. And this experiment when you do, you have to be careful what is the temperature, what is RH, you want to keep everything else same. Okay. Look at only what is the response of this material for an applied load. Okay. So, you can see that on the x axis we are writing time in terms of hour in a logarithmic scale, because we want to study how this material will behave, how stress is generated in this material for a very long time. So, here they have done up to some, let us say 1000 hours. Okay. And then different curve here corresponds to different applied load. So, this one is corresponding to 41.5 highest load, the bottommost curve is for 14 megapascal and anything in between. Okay. At some point of time the load is removed. Okay. Once the load is removed, the system, as we saw before, the system will relax. Okay. So, here this is an experimental data, we are not fitting to any model here, this is a raw experimental data. If it is a Maxwell model, this drop will come immediately and will stay constant. If it is going to be based on one of the SLVS model, it will have its own relaxation times. Okay. So, what you see here is a recovery, the load is taken out, now the material is trying to come back to an extent possible to its original state. So, that is recovery. So, typically you look at both the creep as well as the recovery, right. And so, this is one way of looking at data. This is how you actually measure. When you do an experiment, you set the load and then you look at how strain versus time evolves. Okay, this is a raw data. Sometimes we actually represent the same data in something called isochronous data plot. What it means is, instead of watching over time, you fix at a given time how the material's property changes. Okay. So, here the same data is now replotted into stress versus strain for different times. So, each of the curve here is corresponding to one time. Okay. That basically means in this plot taking one vertical cut. If you take one vertical cut on the left hand plot, these are all corresponding to a fixed time. At those fixed time you have done enough number of experiments, you go to each of this experiment and you measure the stress. This stress is nothing but the applied load divided by the strain, that you are plotting against strain itself. Okay. So, you can see that at 0.1 hours, 1 hour, 10 hour, 1000 hours and 10 power 4 hours, and how the tensile stress and strains are related. Okay. And so there is one place called crazing limit. So, there is a dotted line, that is when the material will rupture. So, crazing basically means it's a network of cracks. If you remember, when the tensile test experiment was shown, when the plastic film was pulled, right, you saw that there is some formation of some holes, and then the holes coalesced and then it becomes rupture, right. So, if you go to microscopic level, even before that you will see formation of micro cracks. Okay. And these micro cracks will propagate, and that will form a mechanism of failure. Okay. So, here we are looking, this dotted line basically tells the limit up to which, beyond which the material would have actually undergone rupture. So, here there are few other curves which represents the effect of temperature. Okay. All these curves corresponds to one single temperature. Okay. And here we are talking about fixed time, but we are changing the temperature. So, as you can see, when you increase the temperature, the tensile strength of the material actually goes down. Okay. So, the material that you are using, you have to be watchful about how much load you are applying, at what temperature you are applying, how long you are applying, what is the RH of the system material, all that will have to be tested. Okay. So, creep test is one which tells you about the material's property for a sustained load as a function of time, how the deformation evolves. Okay. So, this is one way of representing the data. So, we also define something called creep modulus, which is nothing but the stress divided by the strain in a creep test, and you can see the creep modulus is actually measured as a function of time for a different imposed loads. The creep test can be made with a different load, right. The material can be subject to different load. For each load, it will show certain response. So, these curves are basically representing the creep modulus, which is nothing but sigma by epsilon, the applied load divided by the strain, and you can see the creep modulus is changing with respect to time. Okay. And one more thing we do is something called temperature time superposition. You are injection molding a particular plastic, and you want to see whether this plastic will sustain load for 5 years. Okay. Maybe you are thinking about a product, and the product should have a lifetime of, let us say, 5 years. So, ideally you should be expecting that the material should withstand a given amount of load for 5 years. Okay. So, a straightforward way of addressing this question would be, you mold this plastic into a particular part that you want, you know what load it has to withstand, and then 5 years you can wait to see what happens. But generally that is not doable. You cannot do a testing of a material over 5 year long. Okay. After 5 years, maybe this product may not be even needed. So, as an engineer, as a product designer, you cannot do this actual experiment. What you do something called an accelerated testing. Okay. What might happen over 5 year time, you can simulate a similar condition in a small time scale. This basically brings us to what is called this temperature time superposition. What happens in a long time could actually happen at right now at a higher temperature. So, you replace the time with the temperature, right. So, that is what is called a time and temperature superposition, and what is shown here, you can see that this curve C is, let us say, held at room temperature. Okay. And you want to see what happens this for 50 years or so, but you cannot do this testing. So, what you can do is, you can actually increase the temperature and do testing at a higher temperature, okay, for a smaller time, and you can hope whatever suppose if you want to increase, if you want to look at instead of 1 day you want to look at 2 days, the temperature you can actually double it and see. Okay. So, that is called the temperature time superposition. You expect whatever the time will do to the material, temperature can also do the same thing at the temperature. Instead of looking at long time, you look at high temperature. Okay. From there you can say something about how the material will behave in a longer time. It's only a an indicative measure, it is not an absolute measure, because material may behave very differently over time because of various other changes. Right now the freshly molded plastic is virgin plastic or maybe a new plastic, whereas over time there could be oxidative stress, there could be a chemical changes, there may be other effect that may either speed up the material decay, which may not be captured in this superposition principle. Okay. So, some caution is required to do this principle, but looks like this is one way to guess at least what might happen to the material in a long run. Okay, that is it for now, and any questions so far? I know that you are all very tired after the industry visit and a long day. If no question, we will stop here, and tomorrow we have a class at 9.